Okay, embarrassingly enough, I already recorded this lecture, but unfortunately I recorded it on mute. So mute lectures are no good. So I have to do it again. I'm sure you know how much enjoyment and fun it brings to my life. It enlightens my life. Okay, so we're going to speak about graphs. And graphs are, a way to represent relationships, networks, maps, etc., etc. It's essentially a universal tool to model structures. We use it all the time, all over the place. It's one of those structures that are so basic that I kind of wonder why you don't learn about it in high school. It's much more useful than being able to, compute things like the acceleration of a car or some levels of physics that you learn, etc. Anyway, it's a pretty basic structure. You already seen a lot of this stuff, so I'm not going to go too deeply into that. Usually when I speak about graph, think about the Facebook graph, right? Every person that have an account on Facebook is a vertex. Two vertices are connected by an edge if they are friends of each other. In the Facebook case, it's an undirected graph. On the other hand, if Twitter, people follow people, so it's directed, right? So that's kind of things we are talking about. And as we said, our fundamental structure that appear all over the place, and a lot of problems. Once you model them as a graph, you have problems about graph, and you can solve them as a pure problem about graph, like shortest path and so on. And of course, there is a lot of theory behind graph theory. Okay, so an undirected graph, GVE, is a set of vertices V. It's a pair. The first element in the pair is a set of vertices V, and E is a set of pairs of vertices. In the undirected case, it's just a set of two vertices. So the graph on the right, this is the set of vertices, and this is the set of edges. And the set of edges is a bit confusing because it's a set of sets where every set is a set with two elements, which are vertices. Usually when we write an edge, we will not bother to write it as a set UV, we will just write UV. Okay, so that's for undirected. Now, a good example or usage for a graph is to model a state space and a search problem. So here's one such example. Think about, this is known as the three missionaries problem and three cannibals. This problem is pretty old. I think it's like 500 years old or 600 years old. So three missionaries and three cannibals stand on one side of a river, and they have a boat. The boat can hold two people, and they all want to cross the river. Now, the problem is that you're not allowed to leave a minority of missionaries with cannibals because the cannibals would eat the missionaries. Okay, if you don't like this version, think about the version where you're not allowed to leave a cannibal with more missionaries because the missionaries would convert them. Whatever you consider to be undesirable. In any case, this is the rule of the game, right? So we have to move all the three cannibals and three missionaries from one side to the other, where the rule is that the boat can hold at most two people, and in no point in time, in either side of the river, there should be a group that have more cannibals than missionaries. Okay, and they all have to get across. Okay, so how this is a graph search problem? Well, we can write down the configuration, right? How many missionaries and cannibal we have on one side, how many missionaries and cannibal we have on the other side, and where the boat is, right? So I modeled it here. Here state look like, oh, good God. Okay, so one side is the one side of the river, the other side is the other side of the river. M stands for missionary, C stands for a cannibal, and the underscore represents the river, and B is for where the bot is, right? So clearly, you can use this kind of encoding to encode all possible states. I've not written down states that are health states, where the cannibals outnumbers the missionaries in one side, and then the game is over. We got into invalid state. In the beginning, all the missionaries, all the 3 missionaries and 3 cannibals and the boat are on the one side of the river, and we have to get to the destination state, which is that all the missionaries, all the cannibal and the boat are on the other side. So that's the game. Okay, so now you can put down, let's model it as a directed graph. In fact, it doesn't have to be a directed graph because it can be undirected. You put an edge between 2 states, 2 configuration, if there is a way to move from one state to the other by putting a certain people in the boat, right? So for example, from the initial state, if you put 2 cannibal in a boat and across the river, you get to this configuration of 2 cannibals on the other side and a boat here, right? Now, it's symmetric because whatever you sent in a boat, you can immediately send back. It's not very efficient, but you're allowed to do it, which makes that this graph is undirected. And of course, we have the start state, and we have the configuration we want to get to. So this is really a question about, I give you this undirected graph, and I ask you, is there a way to get from this vertex in the graph to the destination vertex of the graph? Right? And this is an easy thing to do, and you can figure out the solution here. Or of course, you can just use brute force to solve it. I solve it manually. It's not especially hard. And this problem, by the way, have a lot of other names. They're all bad names, but the problem is pretty simple. Okay, and it's one of those problems that it's very easy to solve by with a computer. The search, in this case, the search space is so small that you can do it manually. But if the search space was a bit bigger, whatever, right? You write a program, you generate the graph. You have to solve the problem of, can I get from one vertex to another vertex in a graph, which is a very easy problem, as we will see later on. And in fact, you should be already able to solve it. Okay, so in particular, this problem looks to me more a problem about or finite automata than a problem on graph, because this is really, you can think about this as an NFA, and I'm asking, is there a way to get from the start state to this specific state? But, or, if you want, is the language of this automata empty or not? Where the letters are, a letter in the alphabet is how many, a valid configuration on the bot, right? Anyway, so you can think about a lot of problems that we had seen on DFA or NFAs can be interpreted the problem about graphs. So for example, as I just mentioned, is the language empty? Is the language containing all the letters in the alphabet, right? This is essentially a complement of each other, if you think about it. Does M accept W, right? A very easy question if you have a DFA, a bit more tedious if you have an NFA. But those are all problems about graphs, which are pretty basic, and of course we will see how to solve them later on. Okay, here are more exercises that might be a bit more interesting, so think about that. So let's see about the problem. I give you a DFA, is the language infinite, right? So first, if it's non-empty, it's easy, right? Is there a reachable path from the source to the destination? This would be a more interesting question. This is asking whether there is infinite number of distinct paths that reach or walks that start from the source, arrive to the destination. Is the language finite? Also interesting question. Compute the shortest word in the language, if I give you a DFA or NFA. If a language is finite, compute the longest string in the language. Okay, so all these problems are basic problems about graphs. I think you should be able to solve all of them, assuming you had taken CS 225, so you already know basic things about graph. You would definitely be able to solve them by the end of, let's say, next lecture. Okay? This is it.